Okay, let's prove the other direction. So the other direction. So I want to prove that if S does not contain the zero vector, then S is linearly independent. Okay. I think for this direct proof is not so difficult. Okay. Okay. So we do direct proof. So we suppose that S does not contain 0. Okay. In other words, Vi is not equal to 0 for any I from 1 to R. Okay. So we want to show that it is linearly independent. Okay. To show that it is linearly independent, I need to consider 0 equals to k1 v1 plus k2 v2 plus blah 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 and so on until kr vr. Okay, and I want to show that I want to find the values for k1 k2 until kr and show that they are all equal to 0. Okay, it's the only solution for this equation. Okay, so what can we do? We have this information that we haven't used, orthogonal set, and it is in the inner product space V. Okay, what does it mean by it is an orthogonal set in an inner product space V? It means that if I take any two different vectors from this, I take the inner product, I will get 0, right? So this is the thought process. Okay, let's try to think, what if I take the dot product both sides with V1? Okay, if I take the dot product, I mean the inner product both sides with V1, I will get 0 V1 is equal to K1 V1 plus blah 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 until KR VR dot with V1. And we can use the property of the inner product. Okay, the second property, I will get K1 V1 V1 plus K2 V2 V1 and so on until KR VR V1. Okay, and we see that, use blue color, this is just thought process. Okay, this, of course, because we are not taking the inner product of two different vectors in S, it is not 0. Okay, I mean we this part only, sorry. This thing is not 0. Okay, why it is not 0? Since my V1 is not the 0 vector. Okay, how about this? This is equal to 0 and so on and so forth until here it is equal to 0. So everything here will be 0. So I will get this thing only. Okay, is equal to this. What is this? This is 0, right? The inner product of 0 and V1 must be 0. Okay, so we have 0 equals to K1 times the inner product of V1 and V1. Okay, and this V1 and V1 is not 0, so this implies I must have K1 to be 0. Okay, and we can do this. Okay, do this step. We can do this step j times. What I mean by j times is I can also take the inner product with V2, I can also take the inner product with V3 and so on until VR, right? So by doing so, I will get K2, K3, K4 and so on until KR, and all of them will be 0, okay, which is what we desire. But if you want to write one by one, it will be very difficult to write. Okay, it is not so nice. So we can combine all of these cases, okay, into one case. Okay, we just erase this. Okay, this is our thought process. It's quite difficult to erase. Oh no. What is this? Okay, I don't care. What happened? Can I erase? Can I erase? Okay, good. Let's continue. Okay, so this, okay, then what? We just take the inner product with Vj. Okay, where this Vj can be V1, can be V2, can be V3 until Vr. Okay, all works the same. K2 V2, okay, plus and so on until Kr Vr, comma Vj. Okay, for all j. Okay, for all j. But of course, my j must be from 1 to r. Okay, so we do the same thing. This will, I will get 0. I will get 0. For this part, I will get kj, the inner product of vj and vj. Okay, and this implies my kj is equal to 0, since my vj must be positive, as vj is not the 0 vector. Okay, and this works for all j. Okay, this works for all j. Okay. So this means I will have, oops, why I have that thing? I need to erase. Okay. This means k1 equals to k2 equals to blah 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 until kr equal to 0. And we are done, because we only have the trivial solution. Is the only solution. Okay, hence what is the set? S. Okay, S is linearly independent. Okay, done. Hope it is clear.